Topic of this video is critical infrastructure and urban risk. The contents of the training are: definitions of critical infrastructure, C. Overview of urban risks, impacts of risks on urban systems, infrastructure interlinks, critical infrastructures under stress, critical infrastructure resilience and strategies. The learning objectives of the training are: understand the role of critical infrastructure in urban risk landscapes, identify vulnerabilities, challenges and interdependencies across C systems, explore resilience strategies for critical infrastructure. Critical infrastructures, C, are defined as large-scale, man-made systems that are vital for the functioning and continuity of society and the economy. They are complex systems composed of many interacting components designed to ensure optimal performance, reliable operation, and functional safety. An infrastructure is considered critical if its incapacity or destruction would have a significant impact on health, safety, security, economics, and social well-being of a society or country. Cities face a multitude of risks, stemming from natural phenomena, the intensifying effects of climate change, and human-made activities. These risks pose significant threats to the complex urban systems that sustain societal well-being and economic continuity. Thus, urban risk can be defined as the potential for severe negative consequences and associated uncertainty arising from hazards impacting densely populated areas and the critical infrastructure that supports them. Risks to urban systems can be broadly classified based on their cause, whether natural, anthropogenic, human-made, or the result of changing climatic conditions. Human-induced events include technogenic failures, intentional attacks, and structural issues often compounded by human activities. 1. Technogenic and industrial disasters. These include the release of chemical, radioactive, and biological substances, fires in buildings and structures, explosions, ruptures in dams and other hydrotechnic structures, and damages to energy networks or accidents in utility networks. 2. Infrastructure failure. The collapse of buildings and structures or vehicle accidents are considered man-made disasters. 3. Intentional attacks. Cities face risks from public disorders, terrorist attacks, internal conflicts, and modern threats like organized, cyber crime or cyber warfare. Intentional attacks are no longer only hypothetical, increasing stress on systems like the electric power grid. 4. Operational failures. Failures can stem from component aging and failure, sharp load demand increases, and human and organization errors. Anthropogenic influences can also include the consequences of human economic activities that lead to unanticipated floods. Natural disasters and hazards encompass a wide range of events that can threaten urban areas. 1. Hydrological and geophysical disasters. These include floods, ice jams, and flash floods. Flash floods, characterized by rapid onset and high peak discharge, occurring in less than 4 to 6 hours, are a particular type of hazard. Other geophysical risks include earthquakes and landslides. 2. Meteorological and climatological events. Cities are exposed to heavy rainfalls, hail, snowdrifts, storms, and whirlwinds. More severe events include hurricanes and occurrences of intense cold or heat, extreme temperatures, icing, drought, and wildfires. 3. Complex and cascading hazards. Critical infrastructure assets are commonly exposed to sequences of hazards or cascading effects. Examples include flood series over time, flood followed by an earthquake, or a main shock followed by aftershocks. Scour at bridge foundations followed by an earthquake is a specific example of interacting hazards. 4. Other natural phenomena. Risks also include biological events such as pandemics, epidemics, epizootics, animal disease outbreaks, and epiphytotes, plant disease outbreaks, as well as cosmic events like the fall of meteorites or geomagnetic storms. Climate change is not only a source of risk itself but also a factor that exacerbates existing natural hazards. Increased intensity and frequency. Climate change causes more frequent and intense extreme weather and climatic events. Flash flood intensification. The increasing frequency and intensity of flash floods globally are acknowledged to be caused by extreme precipitation levels due to global warming. Transportation disturbance. Climate change challenges continue to be core causes of disturbance in the transportation sector. Risks impacting urban systems lead to severe, cascading consequences across infrastructure, economic, health, and societal outcomes. The exposure of critical infrastructure, C, to hazards has severe consequences on world economies and societies. Physical damage to C, such as bridges collapsing due to scour or earthquakes, deteriorates network and transportation functionalities and requires significant restoration costs. Disruption incurs a dramatic toll on communities' economic growth, resulting in direct and indirect economic losses and significant financial burdens. Health and societal outcomes are gravely affected, with failure in services having a significant impact on health, safety, security, economics, and social well-being. Flash floods, for instance, cause increased mortality and morbidity, as they are associated with the release of non-threshold toxic chemical contaminants into the environment, and cause outbreaks of waterborne diseases due to the presence of disease-causing microorganisms in contaminated water. The high inter- and intra-connectedness of sea means that a local failure can evolve into an unexpected cascade of failures with global, system-level consequences, increasing the exposure to systemic risk. The disruption or destruction of critical infrastructure impacts the whole community. System collapse. Due to the complex and highly interconnected nature of critical infrastructure, a disruption in one part of a system may trigger a domino effect, causing the loss of functionality of other key services. Cascading failures. A local failure can evolve into an unexpected cascade failure pattern with cross-industry effects. For example, strong heterogeneity and connectivity in electric power grids translate into high sensitivity to direct attacks. Functionality loss. Damage to transportation infrastructure, such as road networks, bridges, and rail lines, results in the deterioration of network and transportation functionalities. Following an event like Hurricane Sandy in 2012, transportation disruptions can lead to significant losses. Exposure and capacity. The resilience level of transportation infrastructure is highly dependent on the exposure, location relative to hazard areas, and capability to handle demand, of critical components. When extreme events occur, e.g., a Category 1 storm surge, roads and transit assets in previously regarded safe areas can become impaired. The exposure of critical infrastructure to hazards has severe consequences on world economies and societies. Financial losses. Disruption in infrastructure incurs a dramatic toll on communities' economic growth. For example, economic losses following Hurricane Sandy in New York City totaled $19 billion, with the transportation sector alone accounting for $7.5 billion. Recovery and costs. Events like the 2009 floods in Cumbria, UK, resulted in £34 million in restoration costs after 20 bridges collapsed or were damaged. Direct and indirect economic losses due to landslides affecting road networks are of a similar magnitude. Loss of productivity. Road systems that experience recurrent flooding lose productivity, as potential travelers avoid using them. Risks directly threaten human safety and health, often with consequences amplified in densely populated urban areas. Mortality and injury. Flash floods cause high casualties, reportedly leading to more than 5,000 deaths annually globally. Disease burden. Floods are associated with an increased incidence of communicable and vector-borne diseases. Flash floods have been linked to outbreaks of waterborne diseases such as cholera, shigellosis, and giardiasis. Toxic chemical exposure. Flash floods can trigger the release of non-threshold toxic chemical contaminants into the environment, including lead, Pb, cadmium, Cd, arsenic, and chromium, crossing. High concentration levels of antibiotics, polycyclic aromatic hydrocarbons, PAH, organochlorinated pesticides, OCP, and polychlorinated biphenyl, PCB, have been detected after flash flood events, posing potential cancer risks to human health. Social disruption. Impaired roads following flood events reduce the accessibility and performance of hospitals and other critical assets. They also disrupt the mobility of emergency personnel. Infrastructure interlinks are central to understanding complex critical infrastructure systems, which are composed of many interacting components assembled in a network structure. The sources define two primary types of unidirectional and bidirectional relationships that constitute interlinks. 1. Dependencies, unidirectional relationships. This occurs when a component or system relies on another component or system through a link, but the latter does not depend on the former through that same link. 2. Interdependencies, bidirectional relationships. This occurs when a component depends on another component through some links, and that latter component likewise depends on the former component through the same and/or other links. The relevance of interdependency among critical infrastructures is so high that it has been prioritized by the European Reference Network for Critical Infrastructure Protection, ERNCIP. Stress, in the context of transportation resilience, is defined by the sources as external demands or disruptive events, hazards. The level of resilience achieved is fundamentally dependent on the type and magnitude of the stress applied to the system. Transport infrastructure, which includes roads, bridges, transit stations, and railways, is particularly susceptible to failure due to both inherent structural weaknesses and external hazards. Damage from disasters is a type of physical vulnerability which is commonly described through fragility functions which assess the probability of an asset exceeding an undesirable damage state when subjected to a specific hazard intensity. Location and demand vulnerability can be explained by the two primary characteristics determining transportation resilience: exposure and capacity. Exposure. This denotes the location of an asset in respect to hazard areas. In coastal communities, infrastructure can be exposed to storm surge, and practitioners must consider that hazard areas may expand during a disaster, e.g., Hurricane Ida flooding areas previously regarded as safe. Capacity. This refers to the capability of transportation assets, like roads or bus stops, to handle the demand, often assessed relative to the community population. Capacity issues are crucial during mass evacuation and post-disaster supply chain operations. While the congestion was not labeled as a primary vulnerability mechanism like scour or exposure, it emphasizes the criticality of systems handling high flow demands like high traffic roads, which are roads with high traffic volume, represented by the annual average daily traffic, AADT, are particularly crucial for the supply chain and the community's daily operations. And travel time resilience, in which studies tackle the travel time resilience problem, focusing on how disruptions affect travel efficiency within the network. For example, the collapse of the I-35W bridge, for instance, led to a $0.4 million increase in daily passenger trip costs, demonstrating how physical failure translates to disruption costs similar to congestion. The functionality of water infrastructure is critical for the continuous supply of essential goods and services, and its failure poses severe consequences to urban living and health. Water systems face stress from a broad spectrum of disruptive factors, including natural hazards, like floods and droughts, component aging and failure, and the intensifying effects of climate change as explained before. Challenges that water systems faced under stress are, flooding and drainage can create a major natural hazard that stresses water infrastructure. Cities, particularly those in low-lying areas, face significant flood risks due to factors such as climate change, high rainfall, and suboptimal drainage systems. Supply and basic needs, which is maintaining continuous water supply, is a fundamental task for C, as water supply is explicitly listed as one of the minimal basic needs that must be ensured for the public in case of a disaster or threat thereof. Frameworks for assessing resilience, including the post-disaster restoration process, have been developed specifically for water systems. Also, drought is classified as a climatological natural disaster that presents a risk to urban systems as well. Energy systems are a core component of critical infrastructure, including the generation, transmission, distribution, and storage of electricity, oil, and gas supply. These systems are essential for producing and distributing goods and services such as energy and data. When under stress, the vulnerability and risk of failure in energy C become a priority due to the severe economic and societal consequences that result from disruption. The challenges facing energy systems under stress are complex, covering operational demands, internal failures, and external threats like energy demand spikes. Energy systems must continually extend capacity to meet changing and growing service demands. Grid failures typically refer to system breakdowns that often cascade beyond a single component due to the inherent structural and dynamic complexity of the networks. Fuel supply disruptions. The energy sector includes the supply, transmission, distribution, and storage systems for oil and gas. While the sources classify these systems as critical infrastructure, they primarily focus on the failure mechanisms of electricity networks. However, the overall importance means that disruption in the delivery of essential goods such as energy would contribute to systemic risk. Communication systems, classified under information and telecommunication networks, are a critical infrastructure, C, sector. They are characterized as cybernetic systems that are essential for providing services, producing, and distributing essential goods like data. They are challenged by technological faults, operational stress, and external malevolent attacks. Communication systems are vital for maintaining societal continuity and ensuring effective disaster response. They have two critical roles. 1. Critical role in emergency management. Communication infrastructure is crucial for preparedness, response, and reducing the impact of hazardous events. Early warning systems, EWS. Early warning is defined as the targeted and immediate provision of information to affected people and responsible authorities regarding a disaster or its threats. An effective EWS must be able to issue forecasting and communicate any potential flash flood events to the general public. Reducing fatalities and health burdens. Technologically based EWS can enhance lead times and issue reliable alerts and communications, which helps reduce the number of deaths, diseases, and chemical contaminations in flood-prone areas. Legal mandates. Legal and natural persons have the right to receive an early warning and recommendations regarding action in case of a disaster or threats thereof. Technological integration. Electronic communications merchants providing voice services in a public mobile electronic communications network must ensure compatibility and interoperability with the National Early Warning System. This ensures the early warning of inhabitants using cell broadcasting technology, and this service must be transmitted free of charge. GIS and decision-making. The use of GIS, Geographic Information System, in frameworks provides a highly dynamic tool that allows practitioners and decision-makers to efficiently evaluate resilience indices and incorporate local priorities into disaster mitigation plans. 2. Role in daily operations. The communication sector facilitates essential societal functions. Data distribution. Communication systems produce and distribute essential goods such as data. Global platform. The Internet, a core component of this sector, is defined as a global platform for commercial and social interactions. C systems are crucial because they produce and distribute essential goods such as energy, water, and data and provide necessary services such as transportation, banking, and healthcare. The resilience of critical infrastructure is of paramount importance for the functioning, safety, and economic continuity of communities, particularly in urban environments where risks are heightened due to concentration of assets and populations. Resilience strategies for critical infrastructure, C, and urban risk management are focused on reducing vulnerabilities, absorbing shocks, and rapidly recovering functionality following disruptive events, particularly those involving multi-hazard scenarios. These strategies can be categorized into four main components, often referred to as the 4 Rs, and involve the implementation of comprehensive frameworks, proactive mitigation measures, and specialized tools like early warning systems, EWS, and GIS analysis. Resilience analysis is performed by combining information on hazards, physical vulnerability functions, fragility curves, and recovery models to generate a resilience curve and index. The key components in resilience assessment include the following aspects, often referred to as the 4 Rs. 1. Robustness. The system's inherent strength to withstand external demands, hazard actions, without degradation or loss of functionality. This is quantified using fragility functions which determine the probability of an asset exceeding defined damage states for a given hazard intensity. 2. Redundancy. The system properties that allow for alternate options and substitutions under stress. 3. Resourcefulness. The capacity to mobilize needed resources and services under emergency conditions. 4. Rapidity. The speed at which disruption can be overcome, expressed through restoration functions that correlate recovery time with the functionality achieved for a given damage level. Urban risk arises from the potential for significant negative consequences when hazards, natural, human-induced, or multiple hazards, impact the complex, networked systems of critical infrastructure, C. Critical infrastructure resilience is foundational to urban safety because C failure, or loss of service, can severely impact the health, safety, security, economics, and social well-being of a community. Resilience, defined as the ability of a system to withstand, absorb a shock, and recover quickly, should be guaranteed by the C's design, operation, and management. Given the complexity and strong connectivity of C, e.g., energy, transport, and communication networks, a local failure can trigger unexpected cascade failure patterns with global, systemic consequences. Therefore, interdependencies require integrated risk management, necessitating a harmonized, holistic, system of systems approach to risk assessment that systematically models and addresses these complex relationships to effectively prevent and reduce systemic risk. Finally, planning must align design, governance, and preparedness. This is achieved through comprehensive frameworks that account for multi-hazard scenarios, the asset's robustness, inherent strength, and the rapidity of its recovery. Effective planning involves implementing recovery strategies, resourcefulness, and redundancy in design, and requires a structured process where risk assessment informs decisions made by operators, civil protection authorities, and local governments to prioritize mitigation measures and resource allocation.